Hello everyone, welcome back. So I'm going to do one of the hardest problems from chapter 4 for you. It says right here, it says compute the radius r of an impurity atom that will just fit into an FCC tetrahedral site. Octahedral is not too terrible. That would be this spot right here, halfway in between like any two edge atoms. Now the tetrahedral site is a little bit harder to visualize. If I pick a tetrahedron, which is this shape right here, kind of like a little pyramid, it'll be in the center of that. And that's made up of the atoms in the face for the back, the bottom, the side, and the bottom right corner. So that's the back wall, halfway in the middle of the back wall. That's at the middle of the bottom. That's at the bottom right corner. And this is in the middle of the right side. So we're looking at kind of like an eighth of this cube. I've put too many lines there, now we read it. Either way, it is this shape that we're drawing. It's a little pyramid. And we have this little atom right in the center. Now we want to figure out what the max radius of that atom could be so we can figure it out. Well, there's a lot we have to figure out before we can even get there. First off, we have to remember, well, what is A in this case? Now, this is not my full unit cell. Like, this is what we normally consider A. I've got this like little mini cell right now, so I need to get A in terms of that. Luckily for me, I know that this is the atom on the bottom in the middle, and this is the atom on the bottom at the edge. And in a face-centered cubic cell, those two atoms, they touch. So this line AB is going to be equal to 2r. We also know that this is a right triangle. So we have A here, we have A there, and we know that this is 2r. So we should be able to solve. So let's see, I got 2r squared is equal to a squared plus a squared. What's going to equal 2a squared. And then if I take the square root of both sides, what do I get? Well, I get that 2r is equal to a square root of 2. And if I solve for a, I get a is equal to 2r square root of 2. Okay, so that makes things a little bit easier. Now that we have to figure out, well, how am I going to include this guy? Because it doesn't seem like there's any good lines here. Like, we're always looking for lines where things are touching, but there's, I can, this direction, there's nothing over here. This direction, there's nothing over here. This direction, there's nothing over here. And that is true. And this is where the point you have to realize something that's not necessarily very easy to realize. If we were talking about like an ionic crystal, some sort of like sodium chloride, NaCl, and like this was a sodium cation, we would have a chlorine anion right here, and a chlorine anion right here, chlorine. It would be full of them. Now, those have different radii, but we can also realize something from this. That yes, there is no atom over here in a face-centered cubic cell. However, our little impurity atom, he is floating halfway between this right corner and that back corner over there. And we want to find the impurity atom that's just big enough so that it won't bump into anything. Which means we can pretend like there's an atom over here. We can draw a line straight through the center. And so what we'll get then is that line all the way down from C through E down to that corner, which we don't have a name for. Or, you know what, we'll do it from the opposite corner because I actually have names for all those. A, E to F. Well, that line would be equal to 2 times the radius of my little impurity atom, because we cut through that, plus the radius of this guy, which you can see, plus a radius from one that doesn't exist but could exist over here. Just like theoretically, if we were to flip it around, this guy right here in the center wouldn't move, but we can move this one over here and it still wouldn't be touching. So that line, AEF, that's going to be equal to 2 times small radius plus the big radius. Okay, This is the hardest thing to visualize. So from this point on, it's all just a little bit of trick. So now we have to figure out the other lengths. So we have, let's see, we have length AB right here, which we know that's 2R, 2 big R. And then we have to figure out this length BF, which is just A. So AEF squared, that's the hypotenuse, it's going to be equal to FB squared plus AB squared. This is just telling me that's a line. If I plug in everything I know, well, then I can solve for it. Whoa, jump around them. And it's going to be equal to A squared, which is actually 2R over square root of 2, so let me plug that in there. So 2R, and then AB is going to be 2R, so this would be plus 4R squared. Make sure I do everything right. I think I'm doing it all right. Oh, nope, I forgot to square it. There we go. And that would all be equal to 2 small r squared, small r minus plus big R squared. Or if I do a little bit of rearranging, I would get that R is equal to big R times the square root of 6 minus 2 over 2, which is equal to 0.225, the radius. So my interstitial atom, my impurity atom, can't have a radius that is bigger than just a little bit under a quarter of the larger atom's radius, the host atom's radius. And that would be my answer. Now, all of this is trig. Right here, Pythagorean theorem for a little triangle. Earlier, Pythagorean theorem for a triangle. It's all just triangles for that point. That was a triangle. That was a triangle. Those are true triangles we use to solve the problem. The big thing that you had to realize, was that you had to realize that we could rearrange this and that little floating item in the middle wouldn't move. We should be able to rotate this in any direction we want to, and that little item in the center shouldn't have moved. And that's where we got this from. That's the hard thing to visualize, and it's one of the reasons I wanted to show you how to solve this problem. Other ones are easier, this one is a bit harder. So, thank you for listening. I hope this helps you, and I'll see you all next time. Bye-bye.